Swayam Prabha. Digital India. Educated India.
Hello everyone. So welcome to this fourth lecture of this mineralogy in this lecture series, and in today's lecture we will be mostly talking about the crystal chemistry part 2, and in this lecture we will be mostly covering the electronegativity concept, and we will try to understand what kind of how it is correlated with the different types of bonding, and also we will discuss Pauling's different rules. So if you see the electronegativity, so in the electronegativity in the last lecture we discuss about the electrostatic force that is working on different atoms in the compound or in the mineral, and gravitational force. And when we calculated the ratio of this electrostatic force and gravitational force, we observed that this ratio is 10 to the power 42. So your electrostatic force are the main attractive force that holds mineral together. So your minerals are hold together due to the very strong electrostatic force that is working inside the different these atoms, and all types of bond in mineral depend fundamentally on the strength of electrostatic attraction between particles. And if you see the electrostatic attraction between the atoms, that can be understood on the basis of their electronegativity. So if you will see this presentation, you will see there is some kind of blocks are present in for the different elements present in the periodic table. So this is basically the value of your electronegativity of different elements present in the periodic table. So if you want to define the electronegativity, electronegativity is the value that describes the ability of atom to attract electrons towards it in a compound or in a bond. So basically if we see the how electronegativity varies when we go from left to right in the periodic table, or when we go from top to bottom, first we should understand that how we can define the electronegativity. So if you want to define the electronegativity, so we should basically know two properties, and these two properties are your ionic energy and your electron affinity. So this ionization energy and electron affinity, and this ionization energy is the energy that you require to remove the electron which is present in the outer shell, whereas electron affinity is the energy required to attract an electron to an atom from infinity. So if you want to define the electronegativity, so let's take an example. So suppose if you have an atom, and if that atom is, suppose you have a chlorine atom. So if you have a chlorine atom, so it has a 17 proton. So if you write down the electronic configuration of this chlorine, so chlorine is your 1s2, 2s2, 2p6, 3s2, and then 3p5. So basically if you want to make this chlorine if you want to make this chlorine atom as a noble gas configuration, chlorine need to attract one electron. So because of that, if you see the electronegativity value for chlorine, it is close to 4.1 not 4.1, sorry, this is a 3.16 electron volt. So because of that, this chlorine atom has a very high electronegativity value. If you see the atom of sodium, which has a 11 proton, and if you write down the electronic configuration, so 1s2, 2s2, 2p6, so you have a 10 atom, and then you have a 3s1. So to either this sodium atom can remove one electron which is present in the outer shell this atom, or it can attract total 7 electron to make this sodium atom as a noble gas configuration. So, for sodium it is very easy to just remove the one electron that is present in the outer shell. So, you have a K shell, you have a L shell and you have a M shell. So, in the M shell it has a one extra electron. So, it can remove this electron from its configuration, and then it can become a sodium 1 plus. So, basically it is removing an electron. Because of that it has a very small electronegativity, and if you see the electronegativity of the sodium, so which is close to 0.93 electron volt. So, you see that it depends on what is the electronegativity. So, what is the electronic configuration that basically depends decide the electronegativity property. So, if you have a atom which can attract electron, so it will have a higher electronegativity. So, this is the example. So, if you see this diagram, so what you will observe that when you go, so your sodium atom is here and your chlorine atom is here. So, when you have when you go from left to right, what you observe that electronegativity is increasing. If you see the highest electronegativity, so most of the this blocks are present in this side. So, that is towards the upper right of the periodic table, and if you see the highest electronegativity, so you have this fluorine atom. So, if you see the fluorine this configuration, so fluorine has a 9 proton, and if you write down the electronic configuration for fluorine, so you have a 1s2, 2s2, so 4, and then you have a 2p5. So, if fluorine can take a one electron, attract one electron towards its structure, then it can become a noble gas configuration. So, because of that fluorine has a very high electronegativity. In fact, fluorine has a highest electronegativity in all the elements present in the periodic table, and its electronegativity is around 4.1 electron volt. If you see the left hand side of the periodic table, and when you come from the top to bottom, when you come from top to bottom, what you observe that you have this element which is a francium, and if you see it has a 87 proton, this francium, and if you write down the electronic configuration, you will find that it can easily remove the one extra electron which has in its outer shell. So, the value of electronegativity for francium is close to 0.7 electron volt. So, it has a value of 0.7 electron volt of electronegativity. So, basically your when you go from top to bottom in the periodic table, your electronegativity is decreasing, and you can basically define this electronegativity. So, electronegativity you can easily define if electronegativity you can define if you know the ionization, this energy, and if you know the electron affinity, and there is some constant. That constant is or a conversion factor. So, from this formula you can derive the electronegativity, and basically this concept was introduced by Pauling, and what Pauling did, Pauling derived some kind of relationship with a difference in electronegativity between the two atoms. So, and if you know the difference of electronegativity between the two atoms, and so you can tell from that what would be the percentage of ionic character in that particular mineral. So, he derived, this is the formula, and this formula is basically tells you that how much ionic or covalent character will have in your mineral. So you can derive that if you know the difference in electronegativity in particular compound. If there are two atoms are present in a mineral or more atoms are present in the mineral, and if you know the difference in electronegativity, so so from that you can derive the percentage of ionic character, and that is equal to 1 minus E to the power minus 1 by 4, and in bracket you have a electronegativity difference and the whole term square. So your Xa is basically electronegativity of atom A, and Xb is your electronegativity of atom B. So if you see this table, so in this table you will find the electronegativity value, which is here in the last column. So so in the right hand column, so what you will observe that all the major abundant this cations electronegativity values are given. So if suppose you have, and at the last row we have the electronegativity value for oxygen. So suppose if you have any mineral is forming, and in that mineral you have this cation and anion. So if you take a difference of the electronegativity of these two ions, so you can understand what would be the electronegativity difference in that particular compound. So let's take few example, and so first we will try to calculate the electronegativity of a few minerals which is present or abundant in the earth crust or in the mantle, or these minerals are present in the earth interior. So let's start with the SiO2. So in SiO2 you have a silica and oxygen bond. So we know the electronegativity of silicon atom. So silicon atom electronegativity is 1.90 electron volt. We also know the electronegativity of oxygen atom, and if we take a difference of these two atoms, so we can know the electronegativity difference, that is defined by a delta x. So if you take this difference, so you have a 3.44 this electronegativity for oxygen atom minus 1.90 electron volt electronegativity for silicon atom. If you take a difference of these two electronegativity, you get a value of 1.54 electron volt. So you can take this atom, you can take 1.90 as a atom A, and you can take even this silicon as a atom B, because anyways whatever number you will get, even if you are getting a minus value, because the whole term will have a square, so you will always get a positive value. So your this electronegativity difference is 1.54 in case of your quartz. So when you put this value in this percentage of ionic character, what you will observe that when you put this value in this formula and when you solve this equation, you get this number, and if you multiply this with 100, so that will give you the percentage of your ionic bond in that particular mineral. So when you calculate this, what you will find that your quartz crystal has a 45% ionic character, and it has a 55% covalent character. So you see that your covalent character is stronger in case of your quartz than the ionic character, and we know that if you have a if your material is covalent, if your bonding is covalent in the compound, so it will have a low electrical conductivity, it will have a low thermal conductivity, it will have a higher melting point, it will not soluble in water, and because of that quartz is very abundant in the earth crust. So from this we can calculate your percentage of ionic character for quartz. Similarly, if you have the same two cation or two elements in your compound or in your mineral. For example, if you take a diamond, so in the diamond you mostly made up of carbon. So if you see the electronegativity value for carbon, so carbon has a electronegativity close to 2.55 electron volt, and if even this carbon has a high electronegativity value, but because it is diamond is made up of a carbon atom, so they are made up of the same atom, so the difference will be always 0. So when your difference is always 0, so you will get this number. So whole term will be 0, so it will be 1. So e to the power minus 0 will be 1. So 1 minus 1 will be 0. So you will have a 0% ionic bond. So because of that, even though it has a carbon has a very high electronegativity value, but diamond forms a covalent bond. So you have a 100% covalent bond in case of your diamond. If you take another few example, if you take a halide, that is a NaCl, so we know that the electronegativity value for chlorine atom, and we also know the electronegativity value for the sodium atom. So if you see the electronegativity value for these two atoms, sodium and chlorine atom, and if you take a difference of the electronegativity, so it is close to 2.23 electron volt, and when you put this value in this percentage of ionic character, this formula, you get a 0.71 this percentage of ionic character, and you multiply by 100, so almost 71% ionic character your sodium atom has. So when you have two atom, and when the two atoms have a very different electronegativity values, for example, in case of your this sodium and chlorine atom, so in case of halide, so you see your this sodium atom has a very low electronegativity value, but chlorine has a very high electronegativity value. So when you have this kind of situation, when the electronegativity value is has a huge difference, and when these kind of atoms make a bond, it will be always a ionic, it will make mostly a ionic bond. So because of that, your NaCl make a very strong ionic bond. It has a only 29% of covalent bond. Similarly, you can take another example, for example Al2O3. So in case of Al2O3, you have a 57% of ionic character and 43% of covalent character. So basically you can calculate this percentage of ionic character for any oxide or any compound. So let's talk about the bonding. So when you have, so we will mostly talk about the ionic, covalent and metallic bond. So if you see the ionic bond, so in case of ionic bond, when the two atom which has an extreme different electronegativity value, and when they come together, they basically form a ionic bond. So we saw in case of halide, it is 70%, almost 70% is ionic in character. And another important physical property of ionic bonds are, they are basically they transfer the electrons. So basically your cation which has a lower electronegativity value, that will transfer its electron from the outer shell to the anion which has a higher electronegativity value. So your this kind of minerals are mostly your non-opaque. So this is basically a non-opaque. So you have a transparent minerals. So if you see the salts are mostly transparent. And if you compare this particular NaCl with another phase which is MgO, which is a periclase, or you take an example of ferropericlase. So let's take a like an example of your periclase or ferropericlase. So in case of your periclase, so in the periclase or ferropericlase, they also have a halide kind of salt kind of structure. Okay. And if you calculate the percentage of ionic character in your ferropericlase, what you will find that almost 60% it has a ionic character in case of your periclase, and 50% is ionic character in case of your ferropericlase. So, if you see because the outer shell, you have a +2 charge valency in case of your ferropericlase. So, Mg is +2 and iron is also +2 state. So, it has a +2 electron in the outer shell. So, there the transfer of electron between the cation and anion is not a single electron, but it is a pair of electron. So, because of that, what will happen, that some of the physical properties will change. And for example, if you see the melting this point of NaCl. So, NaCl has a very low melting point. So, at 801 degree Celsius your salt will melt, whereas if you see the melting point of your periclase, so periclase will melt at much higher temperature. If you see the density, density will also change. So, for example, NaCl density is 2.17, whereas ferropericlase density is close to 3.58 gram per centimeter cube. So, you can see this, and there is another one thing which you can see, that is the hardness. So, if you see the hardness of NaCl, so NaCl is relatively its hardness is 2.5 in Mohs scale, whereas if you see the hardness of ferropericlase, ferropericlase is very its hardness is high, it is close to 7 in your Mohs scale. So, these properties, physical properties, will also change if the number of electron that is present in the outer shell in the mineral, and that makes a mostly ionic bond. So, this is the example of the ionic bond. If you see the covalent bond, so basically covalent bonds are in the mineral, where the two atoms have a very high electronegativity, but they are very close, their electronegativity is very close. So, identical in case of, for example, in diamond. So, in this kind of bonding, basically they share a electron. So, in the outer shell electron, there are some sharing of electrons. So, this is an example of chlorine atom. So, when you make a covalent bond between the chlorine and chlorine atom, so there is some kind of sharing of electrons. So, because of that, it makes a very strong bond. So, covalent bonds are, some of the properties are, they are insoluble in water, and it is the strongest in all the chemical bonds. It has a high melting point, it is very hard, non-conductive, and it has a low symmetry and coordination. And this is the example of diamond. So, if you see the diamond atom, they are mostly made this covalent bond. So, in the diamond structure, you have 8 atoms that are placed at the corner of these cubes, and then you have 6 more atoms that are placed at the center of each of the faces. So, you have 6 faces in your cube. So, you have 8 atoms that are attached at the corner of the cube, and then 6 more atoms which are placed at the faces of the cube, and then you have 4 more atoms which are placed inside the unit cell, and this denoted by this green color, and they make this tetrahedral coordination. So, this particular carbon atom is connected with a face centered cubic this atom, and with your simple cubic which are placed at the corner. So, they are connected with 4 different this carbon atom. So, you basically make a tetrahedral kind of coordination, and you can calculate the atomic this packing fraction for diamond if you know that how many atoms are present, and if you can calculate the volume of this particular cell. So, you can calculate that how packly this diamond atoms are packed. So, this is about the covalent bond. And if you see the metallic bond, so metallic bonds are formed between the atom which has a very low electronegativity, but the same electronegativity. So, mostly in the metals. So, in case of metallic bond, like in a covalent bond, you have your electrons are present, make a cluster, and they are present at one particular position. But here your electrons can move at anywhere in your crystal structure. So, it can move anywhere in the crystal structure, and because of that you have a electron which can easily move inside the crystal structure, and because of that metal has an excellent property of conductivity, and so they are very good electrical and thermal conductor. And if you see the if you see their structure, so maximum number of atoms are present in this particular kind of mineral which has a metallic bond. So, these are the some explanation about the metallic bond. And if you see how this ionic and covalent character are changing, so which is defined by the Linus Pauling. So, Linus Pauling basically derive the relationship between the difference in electronegativity and your percentage of ionic character, or here it is a fraction of ionic character. So, basically in the your electron difference in electronegativity is changing from 0 to 3. So, you have some division 1, 2 and 3. So, basically these numbers are your difference in electronegativity is increasing. So, when your difference in electronegativity is increasing, and when you go in this direction in y from bottom to the top, so your ionic character is also increasing. Means that when you have 100% ionic character, which is equivalent to the fraction of 1. So, when you have a fraction of ionic character 1, your material will be completely ionic, it will make a ionic bond. But if the fraction of ionic character is 0, then it will make a covalent bond, and your graph is moving like this. So, if suppose if you take a major cations which are present in your crust and mantle, let us take second most abundant cation that is present in the crust, that is your silicon. Okay. And if you take a difference of electronegativity in silicon and oxygen atom, so that is close to 1.54. So, 1.54 electronegativity difference will be here. So, if you draw one vertical line, so it will intersect at this point, and if you draw a horizontal line and if you try to connect this, okay, so it means that your this silica and oxygen atom will be mostly covalent in character. So, you see almost like 45% of the ionic character or 55% of the covalent character this particular material has. If you take a magnesium and oxygen, if you take this value and if you take this one, this value will be somewhere here, and if you draw a vertical line, it will intersect at this point, and if you draw a horizontal line. So, your mineral periclase will have almost like a 65% ionic character, and if you take a potassium atom and which if you it connect with the oxygen atom, so the difference is 2.62. So, somewhere here, so you have almost like a 77% or 78% of your ionic character. So, if you see most of the cations, if it combined with the oxygen in the crust and the mantle, okay, so it will have a mixed kind of bonding. It will have a ionic and covalent this character. If you take a most abundant mineral in the upper mantle, that is a olivine, if you take a magnesium end member of the olivine, this phosphorite, and if you try to calculate the, if you take a magnesium and oxygen, this electronegativity difference, and silica and oxygen electronegativity difference, and if you calculate the ionic and your covalent character, so your phosphorite will have a 68% of ionic character and 32% of covalent character. So, from this you can easily calculate the ionic and covalent character in a particular mineral which is present in the earth's interior, and you see you will always get a mixed character. So, this is about the your ionic and covalent character, but we also discuss about the metallic bond. So, this particular concept was originally given by the Linus Pauling, but in later in 1940s there were two scientists from two Dutch scientists. Their name was Anton van Arkel and this professor Ketteler. So, what they did, they basically gave a concept in which you can basically calculate the not only ionic covalent, but they added the metallic bond also. So, this is a very famous triangle, and in this triangle is called as a Van Arkel Ketteler triangle, and in this triangle you can basically know that what would be the ionic, what would be the percentage of ionic, covalent and metallic character in a mineral. So, if you see, if you know the difference of electronegativity, so you can easily know that it will be ionic or covalent character, which we discussed in the last slide. But if you take an average of the electronegativity of two atoms, so that will basically define that it will have a covalent or metallic character. If the average is increasing, so you will have a more metallic character. If average the electronegativity, this sum the average of the addition of the electronegativity between the two atoms, if this will decrease, so you will have a covalent character. So, this is a very interesting diagram, and this is I borrow from the open geology material by Dexter Perkins, and what Professor Perkins he did, he basically compiled all the major oxide which are present in the earth's interior or at the earth's surface. So, where they will exist in this triangle. So, if you see the silicates for example olivine, so you also have a iron in your olivine. So, when you take a Mg Fe whole twice SiO4, and when you try to calculate the ionic and covalent character, what you will find, it is very close to the your almost like a 50 or 55% of the ionic character. So, another silicate which is amphibole. So, amphibole is in the it has a more covalent character. So, there is another very interesting correlation with this electronegativity difference. If you take a electronegativity difference, and if your electronegativity difference is increasing, like in this diagram, in this direction it is increasing. So, when you have a electronegativity difference is large, you will have a ionic bond here, and when the electronegativity is very small, in case of diamond, you have a covalent bond. So, if you try to see that how this electronegativity difference have a correlation with a melting point, if you take a ionic character in case of your NaCl, where you have a 70% ionic character. So, if you see the melting point of NaCl, so the melting point of NaCl is 800 degrees Celsius, close to 800 degrees Celsius. But if you take a quartz, so in case of quartz, if you see the ionic character in case of your quartz, so we calculated that is close to 45%. So if we take a melting point of the quartz and ionic character, because their ionic character is less than your salt, so but its melting temperature is high, so you have a 1710 degrees Celsius. Quartz will melt at much higher temperature. If you take a diamond which has a completely zero ionic character and 100% covalent character, if you take that, and electronegativity difference is 0, here is a 0. So, you see that the melting point of diamond is very, very high. So, basically when your electronegativity is decreasing, so you get a negative trend. So, your melting point is increasing. That is very well defined in this particular diagram. So, from that also, if you know the electronegativity of different atoms, so and if you see in any mineral, if you can calculate the electronegativity difference, you can basically know about the melting temperature also. So, this is the advantage of the electronegativity. Electronegativity will tell you many different physical properties, and it will tell about the bonding, different type of bonding which is present in your mineral. So, this is about the electronegativity concept. So, if you see the mineral, okay, so in your mineral basically there are some all the minerals have a crystal structure. So, in 1929, Linus Pauling, what he did, he gave 5 different rules, and if you know these 5 different rules, from that you can basically predict and rationalize the crystal structure of your ionic compound. So, most of the minerals which are present in the your earth surface and in the interior, they have a ionic this bonding. So, it is ionic compound. So, Pauling gave 5 different this rules, and the first rule, which is known as your coordination polyhedra. So, this basically rules suggest that the coordination polyhedron of anion form around the each cation. So, we know that oxygen is the most abundant element in the earth crust and the mantle. If we take in terms of volume percent, so more than 90 volume percent of the earth crust and mantle is made up of your oxygen. An oxygen atom, if you see the size, it is relatively very large compared to other cations which are present in the earth crust and mantle. So, basically your mantle and crust are mostly filled with the oxygen, large this atom of oxygen, and in between the interstitial spaces which is not filled by this oxygen atom, you have a small spaces, and these small spaces are filled with other cations, for example silicon, magnesium, aluminum, iron. So, all these cations are filled in between your large oxygen atom, and oxygen atom is basically responsible for the packing between the cation and anion. So, if you know the radius of this oxygen and if you know the radius ratio of your cation and anion, this basically controls the coordination of a different cation which is present in your minerals. So, to know this first coordination principle, first we have to assume couple of things. The first thing is your anion is always oxygen, okay, and cation is your other elements, and we believe that these anions and cations are assumed to be a very hard sphere. So, in nature you do not have always a perfect sphere, but we assume when we try to calculate and when we try to understand this coordination principle, we have to believe that this anion and cations, they are hard spheres and they are incompressible. So, you cannot compress more. So, this is completely hard and they are always touching to each other. There is another assumption that anions will not touch each other, but may be close enough to be in contact with one another in a limited situation. So, all the anions will not touch, it will not touch to each other. So, sometime only in case of limited situation, some of the anions will touch each other. And third assumption is the cation should surround itself with as many as anion possible to reduce the energy. We will try to understand this. Okay. So, we have a 3 different assumption, and if you see the first situation where you have a, suppose you have a sphere of your this oxygen and you have a 3 oxygen atom, and these oxygen atoms have a hard sphere, and if you take a 3 oxygen atoms and if you believe that these atoms are perfectly sphere in shape, and if you take the center of this sphere, if you take a center of this sphere and if you try to connect this sphere, okay, if you try to connect this point, the center of the 3 sphere, and you believe that these are in a one plane. So, if you have a 3 this sphere of oxygen that are in a one plane, and when you connect the center of these 3 spheres, so it will make a equilateral triangle. So, you have a 60-degree angle and you have some space in between, and in this space you basically have a cation. Okay. So, if you try to connect this point, these 3 points, so you will make a equilateral triangle, and if you see this distance, so this distance is r and this is a. So, you can, because this is an anion, oxygen is anion, so this is Ra and this is Ra. So, basically this distance is your 2Ra, and if you try to connect this point with the center of the sphere of cation, so you will make a 30-degree angle, and this distance will be Rc. So, you can understand from this diagram. So, basically this distance is basically a radius of the cation, and this distance is your radius of the anion. And if you try to draw a perpendicular from the center of this cation sphere of the cation, so it will intersect at this point and you define that point as a C. So, basically you have a ABC triangle and this angle is 90 degrees. So, angle BCA is 90 degree and this angle is theta, and theta is equal to 30 degree. So, basically you can define a cos 30. So, cos theta in this right angle. So, cos theta you can define if you know the AC and if you know this hypotenuse. So, basically your AC is the radius of the anion. So, that is Ra, and this distance AB is basically the radius of the anion plus radius of the cation. So, if you take theta value 30 and if you put this value which is root 3 by 2. So, basically when you simplify this, so Ra plus Rc root 3 by 2 is equal to Ra, and when you solve this you basically get a Rc by Ra which is close to your 0.115. Okay. So, when you have this radius of cation by radius of anion ratio which is close to 0.115, and if you consider you have a oxygen atom. So, you know the radius of oxygen atom, which is close to 1.40 angstrom. So, basically if you multiply 0.115 with 1.40, so you get a radius of the cation. Okay. So, radius of the cation. So, basically if your cation, which is present in between the pore spaces of these three oxygen atom, and if it is a it is connected with a 3 oxygen atom, means it has a 3-fold coordination. So, in that case if you see the radius of the cation, so which is close to this particular coordination principle will satisfy when you have this radius ratio, this cation ratio, cation value is 0.161 angstrom. But if you see the all the major cations which are present in your earth crust and mantle, all this value is relatively larger. So, you do not have any cation in the crust and mantle, major cations which has a this radius of your 0.16 angstrom. You have a larger cations, for example, you have a silicon, titanium, aluminum and so on. So, most of the cations which are present in the silicates or in the minerals in the earth and crust will not have a 3-fold coordination. Only carbon will have a 3-fold coordination in carbonates. So, this basically tells you about the coordination. So, similarly you can take a 6-fold coordination which is defined by this diagram. So, you have a 6 atom of oxygen, and at the center of this pore spaces or at the center of the void you have a solid cation, and this cation is relatively smaller in size. So, if you take all the 4 these atoms which are connecting the cation, so small cation, and if you take it as a one plane, and if you draw it, you will draw your diagram like this in the 2-dimensional view. So, if you draw this and if you connect all the spheres centers, so basically these will make a your square, and these are the apices of the, if you connect the all the centers of the sphere, so it will make a square, and this distance, if this to this distance is basically 2r, and if you take a diagonal, that is AB, so that is your that will define your 2RA plus 2RC. So, basically your AB will be, that is the diagonal will be 2RA plus 2RC, and your if you take this right angle, if you take this right angle, so basically you can define the AB, that is square root of your AC square plus your BC square, and BC square is equivalent to your 2RA. So, 2RA square, and your AC square is basically your also a 2RA. So, when you solve this, your AB will be 2 root 2RA, and from this diagram you can simplify. So, your 2RA plus 2RC, so which is this distance. So, your AB, this 2RA plus 2RC, so this distance is RA, this distance is RA, and this distance is 2RC. So, this AB is also, you can write down 2RA plus 2RC, that is equal to 2 root 2RA. So, from that if you simplify this, so you can get a radius ratio. If your central cation is connected with a 6 anion. So, in that case this ratio will be 0.414, and when you take this anion as a oxygen and you try to calculate the radius of the cation, so this value will be close to 0.58 angstrom. And now if you see this, so 0.58 angstrom, so which is very close to your aluminum. So, it means that if your 6 oxygen, if your aluminum is coordinated with a 6 oxygen, it will make a 6-fold coordination. So, because of that aluminum always have a your 6-fold coordination. So, you see that from this kind of coordination principle you can know about the coordination number, and this basically controls the your crystal structure. And similarly you can calculate the coordination number of a cation which has a 8-fold coordination. So, if you take this kind of example, and if when you have a 8 atoms which are present at the corners of this your cube. So, at the center you have a cation, and when you try to calculate that, what you will find that your radius of the cation will be close to 1 angstrom, and 1 angstrom will close to your calcium, you will have a sodium. So, all this calcium and sodium atom will have a 8-fold coordination. So, basically this principle is very helpful to understand what kind of coordination different cations will have when it connects with a oxygen atom. So, your coordination principle states that how anion and your cation, which basically packed together in the crystal structure, depend on their relative size. So, if if you try to calculate all the radius ratio, so what you will find, so your radius, when your radius ratio is between 0.15 to 0.22, you have a mostly a coordination number of 3. So, if you take this if you take a anion as a oxygen, so if you take, this is basically your radius of cation by radius of anion, and if you take this as a oxygen and you multiply with this number, you will get this number. So, if your anion is oxygen, so the radius of the cation will be 0.217 to 0.315, and in this range only a carbon comes which has a 4+ valency. So, in the carbonate you have a carbon which has a 3-fold coordination. Then if the radius ratio is 0.22 to 0.41, so when you have this kind of situation, you have a 4-fold coordination when you have a tetrahedral coordination, and if you take a anion as the oxygen, then your radius of the cation will change from 0.315 to 0.54, and if you see the radius of the silicon, which is close to 0.26. So, this number is close to 0.26. So, because of that silicon will form as a 4-fold coordination, and of course, aluminum will also form a 4-fold coordination because it is very close to 0.58. If you take this radius ratio, which is 0.41 to 0.73, and if you take a oxygen as a anion, so this radius of cation will vary from 0.58 to 1.024. So, basically you have most of the cations, major cations which are present in the crust and mantle will come in this range. So, you have a calcium, you have a sodium, but see here, because you have a 0.58 in the 6-fold coordination, which is the octahedral coordination, and 0.58 which is a 4-fold coordination, and this number is very close to the atomic radii of your aluminum. So, because of that aluminum has a 4-fold coordination as well as 6-fold coordination. If you see the 8-fold coordination, so your this radius ratio is between 0.73 to 1, and if you take a oxygen as a anion, so this cation radius will vary from 1.024 to 1.40, and in this case you have a iron 2+, Mn2 plus calcium, you have a sodium, you have a potassium. So here you see that you have a situation where your calcium and sodium which have a 6 and 8 fold coordination. So basically your calcium can be in the 6 fold coordination as well as in the 8 fold coordination. But this is not a very precise table, because in nature your this radius can slightly change. Okay, so you will have some distortion in your crystal structure. Because of that, you have a range of this radius ratio, and so sometime some cation can be one coordination number, and in the same cation in the different crystal structure can have another coordination number. So the last one is your this radius ratio is 1. When you have a radius ratio of 1, basically you have a 12 fold coordination. When you have a 12 fold coordination, so in that case you have a this cubic closest packing, and in this kind of packing you have a maximum number of anion, maximum number of oxygen, or maximum number of anion, and in this kind of coordination is very common in case of your metal. So if you have a 12 coordination, so you either have a hexagonal closed packing or you have a face center cubic structure. So if we get a time in the next lecture, we will discuss about that. But when you have a coordination number of 12, that is called as a cubic closed packing. So this is the about the coordination principle. So this is the first rule of your Pauling, and I think the second, third and fourth rule we will discuss in the next lecture. So this particular rule is very helpful, and this basically depend on the relative size of the atom, which are basically the cation which are present in your mineral structure. So this from this rule you can understand that what kind of coordination will have of a different cation that are present in your mineral. So this is about the Pauling's rule, first rule, and second and third and fourth and fifth rule, which is basically your electrostatic valency principle, and then which defines the charge of your ion or cation divided by the coordination number of the cation. And your third rule is basically sharing of polyhedral elements. So this third and fourth rule are more or less similar. So how your different polyhedral are connected with each other, that basically defines the stability of that particular crystal. So we will try to understand this in the next lecture. And then you have a fifth rule, which is rule of parsimony. So which basically defines that even you have a many different atoms present in your crystal structure, but all these atoms will go to the particular structural sites. So even you have 20 different atoms or different types of cations or anions or ionic groups are present, they will go to the particular site. For example, in case of amphibole, so amphibole has in amphibole structure you will find many different atoms are present, but it will go to the particular site. So we will try to understand this second, third, fourth and fifth law in the next lecture. I think this is the good point to stop my today's lecture. So we will meet again in the next lecture, and we will discuss about the Pauling's rule in detail in the next lecture. Thank you.